Hello, everyone, and welcome to Worksheet 21, Video Key. All right, so we are working on alkene addition reactions, and this is the part 3 activity. And we want to remind ourselves of the summary of the way we draw products of syn and anti-addition, using the two models that we described in the earlier parts of the chapter in earlier activities or worksheets. So with model 1, we keep the incoming groups that are getting added across the pi bond in the plane. And then we draw the other two groups that were attached to the alkene as being on a dash or a wedge. So if it's syn addition, then we would just keep the relative orientation of all 4 of these groups the same. So 1, if looking at it from this perspective, 1 would be pointed to the back, 2 would be coming out at you, 3 would be pointed to the back, and 4 would be coming out at you. Now remember, with anti-addition, that's like A coming from the top and B coming from the bottom. And so this is basically undergone free rotation about this single carbon-carbon bond, such that 3 and 4 will have switched directions when you flip this or rotate it 180 degrees. So what we'll see is that when we draw A and B the same way we would draw them with syn addition, we need to switch groups 3 and 4. Notice that 3 has moved to the front and 4 has moved back with anti-addition. And that's just because of the way that we're viewing this, with A and B being in the same relative position as the syn addition. Right? So we always want to remember that we have free rotation about single bonds. For example, this carbon-carbon bond could do a free rotation, and you could have A and B opposite one another by just thinking of taking this whole group and flipping it over like a pancake, so rotating it 180 degrees. So when we do that, the groups 1 and 2 at the first carbon stay the same, but if we take something that's coming out at you and you flip it over, it's going to be pointed back. So what we end up doing is switching these, and we have, instead of 3 pointing out at you, now 3 is going to be pointed back. 4 will point out at you. Right, so this is another way of drawing the anti-addition product that might make a little more sense intuitively, because you can see A and B are opposite one another as opposed to looking like they're on the same side. But this is just 2 different ways of viewing the molecule through bond rotation. Okay, so we just want to keep this in mind when using model 1. And we'll be going through this as the activity progresses. So hopefully that will make more sense to you. Model 2, we place the incoming groups either on a dash or a wedge. Right? So for syn addition, they should go on the same side, either both up or both back. And typically you would get both of those mixture. And then anti-addition is 1 up and 1 down. And of course, the opposite can also happen, where A would be back and B would be forward. And again, so we get both of those. We're just drawing 1 here in this case. All right, so we're going to move on to one of the new reactions that we covered today, which is halogenation. So halogenation, typically we use either Cl2 or Br2, and the stereoselectivity is only the anti-addition product is formed. And remember, that only comes into play when you have 2 stereocenters formed. Of course, sometimes you might have 0 stereocenters, in which case stereoselectivity doesn't matter. If you have 1 stereocenter, you'll always get a racemic mixture. So when we talk about this anti-selectivity, it's referring to the formation of 2 new stereocenters. Specifically, one of the groups gets added to one side of the pi bond and the other group gets added to the other side of the pi bond. That's the anti-addition product. So the first part of the activity asks us to fill in the curved arrows to show the mechanism. Remember that pi bonds are both basic and nucleophilic. So they can do a nucleophilic attack. Remember that bromine is normally nonpolar, but it's very polarizable because of the large atoms. And as something electron rich approaches it, does generate a delta positive, delta negative, which will attract a nucleophile. So you can think of this arrow as like a nucleophilic attack, this arrow as loss of a leaving group. And then in order to avoid a carbocation forming, we'll actually draw a third arrow from one of the lone pairs on the bromine to form a bond to that carbon simultaneously. So essentially we have the formation directly of what's called a bromonium ion. And this is showing the bromine having approached the alkene, which on these two carbons is planar, from the top. But of course, it can approach from the bottom with equal probability, which is why it says there's a racemic bromonium ion, which would mean this is down, down, and then that methyl would be up. Okay, once we have the bromonium ion, this is a 3-membered ring. The bromine is positively charged. So the carbons attached to the bromine are very electrophilic. And then the electrons will flow to the bromine from the carbon-bromine bond. So where should the bromine attack? Well, it is going to do an SN2 reaction, so it will typically prefer the less substituted carbon. Plus, we can see that that carbon inverted here, which is typical of SN2. So we'll draw in nucleophilic attack and loss of a leaving group arrow. And then we see that inversion process taking place at this starred carbon, but no change in the stereochemistry at the top carbon. All right, so it says to prove that inversion is occurring, let's go ahead and assign the stereochemical configurations at the carbons indicated with the star. So on this carbon, first priority group would be bromine, and then the carbon that's attached to the bromine also, and then the other carbon, and the hydrogen pointed back is our fourth priority group. So it would go 1 to 2 to 3. With our fourth priority back, and this is a counterclockwise rotation, this will be coming over here, we have bromine is still first priority, this is second priority and third. Now our hydrogen is coming out of us though. So we should really change this to a clockwise rotation, and this is R. So we see that we have inverted the configuration. So describe why the halogenation reaction is an anti-only pathway. Okay, so it is an anti-only pathway because we go through a 3-membered ring intermediate. That undergoes nucleophilic attack. Via SN2 to give inversion. Right? And I guess we'll say to give inversion of one of the chiral centers. Recall that 3-membered rings, the bonds to the group will always have to be on the same side because it's impossible for bromine to be on a wedge and then so basically be coming out and then also attaching to the back side of the other carbon. The definition, it's a small ring, so if the bromine is coming out, then the other bond to the bromine from the next door neighbor carbon also has to be in the same relative orientation. Because this is syn We get inversion at one of the carbons, and we will end up with the anti. Okay, so next it says to fill in curved arrows, show the mechanism of the reaction below. So we're still forming the bromonium ion, same way that we did, right? So we have the pi bond, attacking the bromine, loss of a leaving group, nucleophilic attack, loss of a leaving group, and then the pi electrons coming back to form a bond with the other carbon. This forms that racemic bromonium ion. And then that's going to undergo SN2, right? SN2 involves both a nucleophilic attack and the loss of the leaving group in the same step. We can see that this carbon has not inverted, but this one has. And the reason you can see that it's inverted is because the first priority group is going this direction, and then it ends up going to the opposite direction after the nucleophilic attack. So just the fact that this bromine is attached in the opposite direction as the new one, we don't actually have to flip the dash, it stays as a dash. And the inversion comes from the nucleophile being attached on the opposite direction. We can just show an SN2. So nucleophilic attack, loss of a leaving group, specifically at this carbon, which undergoes inversion. All right, let's look at the second one, second page. And it says for cyclic alkenes, like the ones that we saw in problems 1 through 3, it's relatively easy to see the anti-addition product because we always use dashes and wedges. For non-cyclic alkenes, it can be more challenging to interpret the product since there is free bond rotation about the sigma bond. So with the double bond, we cannot rotate, right? These are anti or opposite, right? They're trans. But once this becomes a single bond, right, now we have free rotation about that single bond. And so we can draw the incoming bromines looking as if they've done syn addition just by bond rotation. So that's why it's a little bit more challenging. So let's see how we can use our models that we talked about before to show the anti-product only pathway of the bromination of the following alkene. So compare your structures to the product observed in number 4. All right, so we want to use model 1 and model 2 to show how to draw anti-addition products, right? So we might want to remind ourselves what that looks like. So with model 1, the incoming groups are going to be placed in the plane with regular lines, right? And then we're going to end up switching groups 3 and 4 in terms of whether or not they come out in front of you or in back. So that's what we want to do for model 1. Okay, so let's go ahead and see what that would look like. So what are we adding across the double bond? We are adding in the 2 bromines. We can go ahead and add in those bromines. Just like that. Remember, we want to draw the anti-addition product. So you want to look at the model that shows you how to draw the anti-addition product. Okay, so from there, maybe we can even use a different color. Let's draw in the group. So this one, we can draw the ethyl coming out and the hydrogen pointed back. Okay, so we can just dash to hydrogen, the ethyl coming out at you. Remember that with anti-addition, we want to switch this. Right now, it would look like it would be going back along with the hydrogen. Remember that it's going to switch to coming out at you. We want to switch that to a wedge, the methyl. And then the hydrogen, which is coming out, will be switched to the same side as the hydrogen that was going back. Right? So this is model 1, how to draw the anti-product. What about model 2? So what model 2 does is it keeps the carbon backbone in the plane. So notice how 2 to 3 has stayed in the plane with the regular line. And then the anti-addition product will show one group on a wedge and one group on a dash. So let's practice that as well. So we'll do, let's do it in blue, carbon backbone. Right, so we want to just keep this sort of looking like it is, right? We're going to keep the carbon backbone in the plane. And then we're going to add in the bromines on a dash and a wedge. And so you can choose which one you put on which side. We have bromine coming out and bromine going back. Would we also get the enantiomer? This. Yes, right. We can also get back, front, forward, just equal probability. This one also has 2 chiral centers being formed here. Would we get the enantiomer? Absolutely. That would be the exact opposite at the 2 chiral centers. All right, so let's use those models to fill in the empty boxes below. And now it says you just have to use model 1 or model 2, whichever one you feel more comfortable with. Totally okay either way. I am going to, for the ones where we're drawing products, I'm going to do it both ways, just for the key so that you have it both ways. Although usually I do prefer model 2. So a lot of times if I'm given the option, I'll do model 2. Okay, so how do we draw products here, right? So one thing we want to remember is the first thing we always look at are the reagents, right? And remember that halogenation, right, gives us anti-addition. And you might have noticed that we haven't been talking about regioselectivity. And that's because the both atoms get a bromine, so we don't have to worry about which atom gets which, right? Because they both get the same atom. So we don't have to worry about regioselectivity in halogenation, but we do have to worry about stereoselectivity when 2 stereocenters are being formed, which will be the case in all of these examples. Okay, so using, I'll just draw like an extra, we should have done. Just want to do it using both models, right? Just for the answer. So we'll do model 1, model 2. All right. So with model 1, remember that we typically like to draw the 2 bromines in first because they're the easiest to draw there in the plane. So we'll go ahead and add in the 2 bromines getting added across the double bond. Remember that we need to make sure we do anti-addition here. So we are going to add in these groups. If it's pointed this way, we'll just have it pointed back, that methyl, and then this group will be coming out at us. And then remember with anti-addition, we switch the other side, right? So it looks like it should be pointed back, but we're going to end up switching it because of the way the bromines are written like a syn addition next to each other. Okay, so that's an ethyl group on this side. And if you want, you can draw in the hydrogen, although that's optional, pointed back. That would be this hydrogen. Okay, so that would be model 1. How do we do this with model 2? So with model 2, recall that we keep the main carbon backbone in the plane. Okay, so I'm just going to kind of draw this exactly as I see it, like this. And then I'm going to add in the bromines, one pointed out and one going back. So I can do that in a different color. And then note that this methyl would then be pointed back here. You can just write CH3 or just leave it like that. So that would be model 2. Remember that these will always also give. Okay, so it can actually be pretty tricky going back sometimes, right? Because now we need to look at the relative positioning of these R groups, right? The carbon-based groups, and then figure out if I should have started with a trans or a cis alkene. Or you can think of it as an E or a Z alkene as well. Okay, so remember that fluorination is a halogenation reaction. It's going through anti-addition. So that means that we would have switched one side, right, from the original positioning. So for example, when you see the two groups on the same side and it went through anti-addition, then those two groups would have been on opposite sides before. So in this case, we're seeing the opposite. These are on opposite sides, having gone through anti-addition. And that tells me that this was originally a cis, or you can think of it as a Z alkene. So hopefully that makes sense to you, right? You want to see that this is the anti-addition product, right? That's really important. So anti-addition product. Which means that these look like they were on opposite sides, but we rotated this carbon-carbon bond in order to get these to be next to each other. So originally, this should have been on the same side, right, as the ethyl. Put them on the same side, then that makes this alkene. You can go back and study your models and hopefully be able to understand that or see the difference from that. You could think of this as, right, from the model, this is, think of it as 2 and 4, right, because they're both on the same side, so 2 and 4, right? What happens to 2 and 4 in the product? They end up opposite. One's coming out at you on a wedge, one's going back at you on a dash. So that's the same thing here. One's coming out at you, one's going back. So they initially started on the same side, ended up opposite. Okay, so moving on to the next one. Remember that all of these are anti-addition products. So this one, you know, and all of these cases. So, but the ring actually makes it much, much easier, right? There's only one way the ring can have a double bond. 5-membered rings can only accommodate a cis double bond. And drawn this way, of course, the bromine is anti, and they're shown that way, which is great. All right, so that one with the ring actually is much easier. Okay, so same thing for this one, right? We want to draw it with model 1 and model 2, just so that they're both in the answer. Remember, you have to just pick your favorite way to be able to do it that way. But it would be even better, actually, if you really understood both ways. That way, no matter which way the product is given to you, you can recognize it for like a multiple choice example. Okay, so let's go ahead and draw anti-addition again. Remember, we kind of using our first model, no matter if it's syn addition or anti-addition, just add the two groups that are getting added across the double bond, drawn in like this with just regular lines. And then we come over here and look and see what will be coming out at you, which is methyl, what will be pointed back, right, which is the ethyl group. And then recall for anti-addition, these get switched. Right, so the ethyl group will be pointed back, the phenyl will be coming out at you. All right, and then for the second one, the second model, we're just going to look and see what's on the zigzag and keep it like that. We'll just do that. Just a hexane in this case. And then we'll add in the bromines. Remember, one needs to be going out at you, one needs to be pointed back to the anti-addition. So you choose which one you want to do. It doesn't matter. I may draw the enantiomer of the one that you draw, but it's still the same as long as you write plus n. Okay, so I'm going to do dash wedge. And then I like to come back and see, okay, what else was here? That needs to be, that gets pushed to the opposite direction. So if the bromine came in from the top here, then that means the methyl will be pointed back. And if the bromine came in from the back on this carbon, then the phenyl will be pushed up. All right. Then always, we're never doing an enantiomer selective reaction. We're always getting a. Okay, let's look at the next one. Develop a strategy that would help you solve the following problem. Okay, so this one is a bit tricky because notice how the halogens are actually drawn as opposites, right? They're not drawn the same way we would have drawn them from model 1. So we could actually flip it. So that's one strategy, is just to do a rotation, right? Rotate one side, keep the other side steady, and then see what it would look like. So typically in our model, like to see the halogens in this orientation, which would mean that anything that gets flipped over switches from a wedge to a dash or vice versa. So that's why I've moved the up phenyl to the down phenyl. So those are equal. So that might actually help you see the original orientation. Because remember, this is undergoing anti-addition. Okay. So if it's undergoing anti-addition, then these got flipped from their original. Right? They look like they're on the same side, but that means that they would have been on opposite sides of the pi bond originally. Or because it's anti-addition, you could think, oh, these are nicely drawn anti. Then the relative position of this would be the same, right? One would be on one side of the pi bond and the other would be on the other side of the pi bond. So either way, hopefully you came up with the trans or E alkenes. Right? Because these, they look like they're on the same side, so they should have started out on opposite sides when you're undergoing anti-addition. All right, moving on to halohydrin formation. So halohydrin formation is very similar to halogenation. We're just in adding water to the reaction mixture. And when we do that, water outcompetes bromine as the nucleophile to do the SN2 reaction. And the reason why is there's a solvent amount of water present, and there's very little bromide present. So even though bromide is a better nucleophile than water, it gets outcompeted by the fact that water is just surrounding this molecule. So let's draw the mechanism in first. So again, we'll start off with the same arrows we did before to draw the formation of the bromonium ion. We have the racemic bromonium ion, and now water will act as a nucleophile and do backside attack. And get the oxonium ion that needs to be deprotonated in order to get a neutral molecule. I actually need to draw in another water to do that final proton transfer. Okay, those are the arrows, and it says what is added to the more substituted carbon of the alkene. So here, what gets added there is an OH group, right? And can we describe this as Markovnikov or anti-Markovnikov controlled, right? Well, technically the definition of Markovnikov, right, is the hydrogen gets added to the carbon with more hydrogen, right? So I would say no, it cannot, because we are not adding a hydrogen, right? We're adding the OH group and a bromine, right? Or a chlorine. So since neither is a hydrogen, right? No, you don't classify as Markovnikov or anti-Markovnikov. So we just need to remember that the OH gets added to the more substituted carbon and the halogen gets added to the less substituted carbon. So that does mean that the reaction has regioselectivity, because if the OH got added to the less substituted carbon and the bromine the more substituted carbon, that would be the opposite constitutional isomer, also known as regioisomer, and therefore we would get a different product. So it selectively forms the OH getting added to the more substituted carbon, and we want to explain why that is, right? So we have this bromonium ion intermediate, but the carbon-bromine bond to one of the carbons is weaker than the other carbon-bromine bond. And the one that's weaker is the one to the more substituted carbon, because that carbon can more effectively handle a delta positive, right? So this one is lower potential energy, right? Because the partial positive charge is on a more substituted carbon, which is more stable. So how does this explain the observed regioselectivity? Actually, I would not call it the Markovnikov control. Just notice that exact terminology in there. Okay, how does this explain the regioselectivity? Well, the fact that there's a more significant partial positive charge here means that water, which is the nucleophile, right, will attack the carbon with greater positive or electrophilic character. Because again, it's going to go through a lower energy pathway that way. All right, nucleophiles that are similar to water can be added to the bromonium ion intermediate. Predict the product of the following reactions. Okay, so first we're going to use water and we're going to predict the product. So recall that we are doing anti-addition of bromine and OH across the double bond. The OH will go to the more substituted carbon. We want to make sure we get the regioselectivity correct and the stereoselectivity correct. So let's go ahead and draw in the product without any, without the groups first. So we just take away the pi bond, right? And then we start adding the group. So remember that the OH is going to get added to the more substituted carbon. And it doesn't matter if we place that on a wedge or a dash, because the enantiomer will also be formed. But whatever we do, we have to do the opposite for the halogen. So the bromine then go on a dash, and then we write plus the enantiomer. Okay, so we want to do the same strategy for here as well. We want to remove the double bond, add the bromine, and in this case, we're going to add in an O-methoxy. So some people might want to draw in an OH instead of an OMe. Remember that the final step is proton transfer. So this proton will be removed through electron transfer. So the group that we want to add is actually this one, not the OH. So, and that's going to go on the more substituted carbon. So we can do that. But think about the fact that this is not going to become a chiral center. So I'm actually just going to go ahead and add that in. Here it is. You can write O line or OME, right? And I'm not going to worry about placing it on a dash or a wedge because I don't actually have a chiral center. The bromine will go here. This is going to become a chiral center. So I can either add this in on a dash or a wedge, but remember that we always get a racemic mixture. Get an equal mixture of both enantiomers. Okay, moving on. Next, we're going to be adding, instead of a bromine, we'll add a chlorine. And it's just going to be SH, right? Because one of these hydrogens will get deprotonated. That will end up on the more substituted carbon. So I'm going to draw that in. And then I'm going to place the chlorine here on the less substituted carbon, right? Dash or wedge, doesn't matter. The relative positioning of anti is what you need to make sure that you do here. So if I place the chlorine on a dash, that means the OH group has to be on a wedge, which in this case is an SH. That as well, which pushes this methyl back. Plus the enantiomer. And lastly, right, we have the 5-numbered ring. And we want to place, again, the bromine will go on the less substituted carbon. Right, the other group will go on the more substituted carbon. That will push the methyl back. And this will be SET. Right, remember, the hydrogen gets deprotonated. Okay, so notice that I have done, whenever I draw products, I generally use model 2. That's just because that's my preference. But you could as well have drawn these products using model 1. So we can do that as well. It's not very common to see a ring drawn with model 1, right? So I think I will skip that. I mean, it could be done. You could keep these in the plane and then have these on wedges, for example. But I'm just going to say not common to use model 1 with cyclic substrate. Right, so for the first and third one, I don't think I'm going to bother trying to draw that with model 1. You could do it, but it's not common to see it that way. Okay, so but with these, it is a little bit more common to see it drawn that way. So remember, we want to do anti-addition. We want to see what groups are getting added across the double bond, and then place those groups right in the plane in that sort of orientation, right? So we can just kind of go sort of draw this in to start with. Remember that we're going to look and see what's getting added. Okay, so bromine and OME. So I'm going to do bromine and O and E here. Or you could just do O with a line attached. Either one is okay. And then we want to go ahead and put in the relative positioning of the groups. Right, so this would be a wedge. And then technically, because it's anti-addition, we would switch these two, but they're the same group. So it wouldn't really matter. So we can just draw one. Just do regular lines or just draw one coming out, one going back. So again, these could just be regular lines because that's technically not a chiral center. And so we'll just say with acyclic products, And then, so we're going to do the bottom example here again. We're adding chlorine and the thiol group. So we'll notice that the thiol group got added to the left over here. So we draw that one over here and the chlorine here. And then remember that we're doing anti-addition. So we'll keep this one the same. Methyl coming out of tube, ethyl pointed straight back. And then we want to go ahead and switch this, right, because of the anti-addition. Also, okay. And again, these are also plus the enantiomer. In this case, only this is a chiral center, so it's only the enantiomer of one chiral center. In this case, two chiral centers. So the enantiomer of both, the mirror image of both. Okay, so different ways of doing it. Moving on to the next question. Provide a mechanism for the following transformation. Numbering atoms for a complex mechanism allows you to see what bonds you need to make or break. So you can see that they've numbered here, so we can just keep that sort of number, just the same numbering system up to number 7. So we'll see that the bromine gets added to carbon number 7, right? And then this thiol actually does attack at carbon number 6. So we want to form the bromonium ion in the first step and then have it be attacked by water. Excuse me. Normally you would attack by water, but intramolecular reactions are faster than intermolecular reactions. So it looks like water gets outcompeted by the sulfur, right, which is already attached to the same molecule. So let's go ahead and draw in the bromonium formation of the bromonium ion. So the pi bond attacks loss of a leaving group, and then lone pair on bromine forms a bond to the more substituted carbon. So all of that's happening in one step. And I noticed that they haven't drawn any stereochemistry here. Technically, this is a stereo center, but no stereochemistry. So I'm just not going to worry about it. I'm just going to draw regular lines in this case. So it looks like they don't really care so much about stereochemistry. So if I do that, and I'm kind of wanting to make it look a little bit like this, and I'm just going to have the sulfur, and I'm going to have 2, 3, 4, 5, 6, and then the bromonium ion. Now again, this is a chiral center, right? So this would be on a dash or a wedge, but it's going to be a mixture of both. Right? There's not going to be a preference one over the other. If we want to do the same numbering, we can do that. Make sure we've got all of our carbons drawn in. All right, so this is going to go ahead and do nucleophilic attack to form a ring. And it looks like that sulfur is going to be attached to carbon number 6. And that's because 6-membered rings are really stable. And so they're easy to form. And we'll do loss of a leaving group. So this is an SN2 process here. So now we are going to form the ring. And start making it look like the product here. The only difference is that we still have hydrogen attached to the sulfur. So that still needs to be removed in a final step. So we can use water. Why not, right? Water is there. It can act as a base to do our final proton transfer. Get to the product here. And we've got a little bit of H3O plus bipolar. And then we also form some bromide, yeah, from the leaving group on the first step. Okay. Epoxidation. So we are going to start off with the first step of the anti-dihydroxylation reaction, which is epoxidation. And epoxidation actually undergoes syn addition. So we don't get the anti-product. It's just impossible because of the size of the ring. It's a very small ring for the oxygen to be simultaneously attached to one side of the ring and the other side at the same time. So it has to be on the same side. So either both up or both down. Okay, so say 3-membered rings are small. Oxygen can't attach in anti-orientation. So if you try to make a model of something like that, it's just impossible to do. So that is why. Plus, another reason would be that the bonds from the oxygen to both carbons are formed simultaneously. Right? Bonds from both carbons to the oxygen are formed, you can think of it as simultaneously or concertedly, right? All in step. Okay, let's go ahead and draw in the mechanism. So the weakest bond here is the oxygen-oxygen bond. Remember when we talked about radical chemistry, that bond was relatively low energy, weak, it's easy to break through either light or heat. For the same reason, we're going to be able to break that bond easily through nucleophilic attack. So the pi bond, which is nucleophilic, can go ahead and attack, and it will selectively attack the, this oxygen because this group is a better leaving group. Think about the electrons here, right? If I add them as a lone pair, they'll be resonance stabilized. So that's why if I attacked this oxygen, I would have to have OH as a leaving, which we know is not a good. So then these electrons can come around. This is like a resonance arrow. It's like an allylic lone pair. So I could deliver these electrons as a lone pair on that oxygen, or I could take them, understand that they'll be on oxygen, and they'll do a proton transfer. There's a lot going on here, right? And then these electrons can be used to make the other carbon-oxygen bond. So 4 arrows, all with a concerted reaction to form that epoxide. And it gives us a nice, stable carboxylic acid byproduct. Okay. So use either model 1 or model 2 to fill in empty boxes. Okay. So again, for the drawing the product, right, I'm going to want to do both of them just in case you did it through. I don't want to pick one and your answer cannot be able to match one. Okay, so model 1, model 2. Okay, so remember that this is occurring, the epoxidation is occurring in a syn-selective fashion. So we want to make sure that we remember that when we're trying to draw products. So I'm just going to write syn over here as a nice reminder to us. And what is getting added across the double bond? This one's kind of interesting because what's getting added across the double bond is just an oxygen that both carbons are attached to. So that's kind of different from the previous examples that we had. So we can actually draw that attached, right, to both carbons instead of just attached to one with a regular line for model 1, right? No dash, no wedge there. Okay, then, right, we can add in the other groups, right? This one, you could do it with a dash and a wedge, right? Or you can just do regular lines because technically, right, that is not a chiral center, right? So we'll say for here, say dashes with a dash wedge. Okay. Or we has regular bond since it's not chiral. Okay. And then the other side, though, is a chiral center. And as it's drawn right now, would be pointed back. Okay, so we'll go ahead and just keep that consistent, although, of course, we would also get the enantiomer for when the epoxide formed from the opposite face of the pi bond. So I just want to make sure I mention that. Okay, what would it look like in model 2? So in model 2, there's a long carbon chain, and I like to just sort of keep that as is, right? And then we'll add in the epoxide. So you either want to have both a wedge or both a dash, right? So for example, you could comment to just do wedges, right? Again, this is not going to be a chiral center, right? So you could draw this as a dash, or you could just leave it as a regular line. It doesn't really matter. Again, I guess I'll make a note of that as well. Right here, could draw one dash. But it's not really critical because it's not a chiral center. This one, however, is, so we'll want to make sure to do that. And so it also could be. Okay. Now, right, maybe the more tricky part is going to be figuring out how should we draw the original alkene, right, before the epoxidation. So notice that over the arrow, it might say MCPBA, which is just a specific type of peroxy acid, or it could just say RCO3H, or it could even give an R group like methyl and the CO3H. So different types of peroxy acids can work. MCPBA is just a very common one because the byproduct, which is perachlorobenzoic acid, is solid and it will precipitate out of the dichloromethane, which is the common solvent used in this reaction. So it's easy to remove the byproduct. So it's kind of has that advantage, which is why it's commonly used. Okay, so we just want to recognize these basically meaning the same thing. So remember that this is a syn addition product, right? And so these groups will not have undergone rotation. So if you're looking at them on the same side, then you should draw them the same side. Okay, so start with this one. This is not going to be a chiral center. So notice how they did a dash and a wedge here, even though this is not a chiral center. That's totally okay to do. You can just draw them as single lines or a dash and a wedge. Technically, this is more accurate for the 3D real spatial relationship. That's a tetrahedral carbon. Okay, so in this case, we don't really need to worry about cis or trans for the alkene since two methyls are identical, right? There is no such thing as cis or trans. So basically, we have the two methyls, have the double bond, and it doesn't matter if you place methyl here or there, it will really be the same. And over here, right, again, syn addition. Notice how the groups are on wedges now, right? So this is like drawing the product with model 2. So this is still giving us relative stereochemical information though. To note that well, I guess in this case, not really, since both of these are phenyl, right? One is on the same side as methyl, the other is on the same side as the chlorine. Since they're the same, it wouldn't really matter which one you drew where. Okay. Provide a synthetic route to the following target. So at this point, I want to introduce to you the concept of retrosynthetic analysis. So retrosynthetic analysis means that we're going to work backwards from the product back to the starting material. So instead of working in a forward direction, we kind of work our way back, targeting key products along the way. Okay, so I'm going to say let's first do a retrosynthetic analysis. So we have an epoxide, right? Epoxides are made through epoxidation using MCPDA or another peroxybenzoic acid. So retrosynthetically, we'll use one of these retrosynthetic arrows, right? So moving backwards. We know that we make epoxides, right, from alkenes. So that's the forward direction, right? We would use MCPDA from the alkene to get the epoxide. So looking at the relative positioning here, we know that this is undergoing syn addition, which means that these have the same relative positioning as the alkene. So these are going to be starting from a trans alkene. We want to make sure to draw that and not the cis alkene. Okay, and then now we are a little bit closer, right, to the product. How do we make double bonds? Think to yourself, how do I make an alkene? Well, we make an alkene through an elimination reaction, right? So if we're going to do an elimination reaction, we need to have a good leaving group to eliminate. So perhaps we had a bromine, which is a great leaving group, right? Then we would be able to do an elimination, get the Zaitsev product, right, to get that alkene. And then how would we add a bromine on an alkane? Well, we're going to do radical halogenation. And since this is the most substituted carbon and these are equivalent, the bromine will definitely go there. All right, so this is our retrosynthetic analysis. So then in the forward direction, we'll provide the same intermediates, right? We just need to provide now the reagents to get to product. Okay, so in the forward direction, we said we wanted to do radical halogenation. So we're going to do bromine and light. Now we want to do an E2 elimination. And we want it to undergo Zaitsev regioselectivity. So in this case, I would use a small base. I want Zaitsev regioselectivity. So sodium hydroxide, sodium methoxide, or sodium ethoxide. Good. The bulkier it gets, the less substitution but we don't want to go so bulky that we get the Hoffman product. Okay, and then epoxidation, right, utilizes MCPDA or RCO3H. This is oxidation. next reaction is really just a continuation of the previous reaction. So once we do use MCPBA to form the epoxide, then we use H3O plus, and we end up with the anti-dihydroxylation product. So the mechanism, right, is going to be the same that we drew before. So pi bond attacks oxygen, electrons flow around, get a proton transfer, and you can start from either the lone pair or the pi bond. Right? Probably should have started with the pi bond. Simpler, less arrows that way. Okay, then right, we have the oxide intermediate. And that's going to be treated now with H3O plus. Right? So this will do a proton transfer. Remember, acids protonate things. Right? So we probably protonate our substrate. The oxygen picks up a proton. Now the oxygen here has a positive charge, which makes the two carbons that it's attached to electrophilic. Because nucleophiles would rather attach to the carbon, and then the electrons from the bond can go to relieve the positive charge on the oxygen. So in this case, it really would not matter where the nucleophilic attack comes from, because this is symmetrical oxide. But we could, since we're looking at the bottom carbon undergoing conversion here, we'll just have it attached to the bottom carbon. Okay, and then we want to have following last proton transfer to get a neutral product. And we end up with racemic, right, anti-dihydroxylation product. Okay, and then, so fill in the curved arrows. Explain why the above dihydroxylation reaction proceeds by an anti-only pathway. Right? Describe the reaction pathway in box that's empty. Provided. Okay, so this is an SN2 reaction. Right? So again, we're going through SN2 on a three-membered ring, right? Three-membered rings must be formed syn. So when you do SN2, right? So backside attack, conversion provides the anti-product. All right, what about syn dihydroxylation? So syn dihydroxylation uses either osmium tetroxide or potassium permanganate. The potassium permanganate structure looks a whole lot like osmium tetroxide. So potassium permanganate actually looks like very, very similar to osmium tetroxide. You can see that there's a metal and double bonded to oxygen. It's just like with the osmium. So that's why they react similarly. So what does this look like? Right? Well, one side of the pi bond will attack one oxygen. Electrons will flow to reduce the osmium. And then we have the other oxygen being used to form a bond with the other carbon. This gives you syn product, right? These methyls were opposite, so they stay opposite. So this is called the cyclic osmate intermediate, which eventually undergoes cleavage of the oxygen osmium bond through a reductive workup. And that's how we end up with the syn addition product. Okay, so we've filled in the arrows for the first step, what it wanted us to do, and now it wants us to fill in the boxes, right? Consider dihydroxylation. Is it going to be syn or anti? And what we need here to fill in these empty boxes. Okay, so first of all, we of course want to consider the reagents and remember what they do. So MCPBA followed by acid is the anti-dihydroxylation product. Osmium tetroxide is syn, potassium permanganate is syn. We'll have to look at these later since we can discuss the reagents. So that's good to know. So we can draw the product of this anti through either model 1 or model 2. Okay, so what would it look like with model 1? Well, remember that we are doing dihydroxylation, so we should add OH, OH across the double bond. And then, since this is anti, right, we need to flip one of them over. So this looks like this methyl would be pointed back, right? And then this one's going to be flipped over, coming out at us. Okay. Model 2. Model 2, right? For model 2, I like to keep the backbone where it is. Easiest way to do it, right? If in this case, it is not the normal zigzag, right? It's instead kind of like this, but that's okay. We can. Okay, and then we want to add in again the 2 hydroxyl groups anti to each other, right? So one would get down and the other one. And of course, this is not a meso compound, right? So this is going to be plus the enantiomer in both cases. 2 different ways of drawing that product. All right, so what about syn addition, right? So this one is like extra tricky here, as it's reagents that give syn addition, but they're drawing the OHs opposite one another, almost as if they did anti-addition. So for me, I would probably like to get this in so it looks like a product from model 1. So what I can do here is I can draw the OHs like they're in model 1, right? And then flip one of them over so it gets that way. That would end up getting them both on the same side. Okay, by the way, you might have noticed that there's an internal plane of symmetry here. So this is actually a mesocomb. So this one does not have an enantiomer. You didn't have to know that to do this problem, but I just wanted to point it out since I noticed. Okay, so this, at least now that we have it looking like this with the 2 incoming groups in the plane here and drawn next to one another, knowing that this underwent syn addition, that should help us be able to draw in the product here. So in this case, these 2 will be on the same side. You could draw it exactly like this, or you can draw it slightly differently. Okay, so these, again, same side, so same side, syn addition, nothing got rotated. All right, moving on here. Potassium permanganate, this reaction has to be done cold, right? However, if it's kept cold enough, potentially it can work to do the same thing osmium tetroxide can do, although it does suffer from more side reactions. So it's a little less synthetically useful. Okay, so we know that this underwent syn addition, right? This is nicely drawn as we would draw a product from model 1, which means those are on the same side, so they should have started out on. All right, let's look at this one. So here's a trick, right? now we have to figure out what is the relative orientation here, and then which reaction condition, either syn or anti-dihydroxylation, is necessary to get me there from the given alkene, which is either cis or trans, in this case trans. So it, it may help you, depends, right, on how you like to do it, but it may help you to rotate this so that we have these two groups on the same side. So in that case, I would actually flip over the left half of the molecule just so that I can nicely get it in the orientation I'm used to looking at, right? Which means this one stays back and this one comes out. Right, so those are just two different ways of drawing the same thing. So now you can see that these are opposites, right? And these are opposites. So if you start with opposites and you want them to stay opposites, then you need to do syn dihydroxylation. So we should either write osmium tetroxide NMO or potassium permanganate under basic conditions cold. Okay, and the other way to think of it is these look like they've got added anti, but these are on the same side, right? So if I had started from cis alkene, I could have done anti-dihydroxylation to get to this product, but since I'm starting from the trans alkene, I need to do syn dihydroxylation. All right, so let's look at this one. This is a little bit different. Stereochemistry is different on this carbon, right? Which probably tells me that you want to do the opposite, right? Because if you would rotate this one, then you would see that both methyls, right, are on the same side, but they started off on opposite sides. So our rotation has to have occurred in order to get them to appear syn, right, even though they started anti. So that means we had to do an anti-dihydroxylation. So we need to do NCPA followed by H3O+. Okay, notes here. Right, starting from trans for E. Right, and this is now same relative orientation. I'm trying to think of the exact words I want to write. Relative orientation as reactant trans, which means we needed to undergo syn, right? These are opposites and they ended up with opposite relative orientation. Now they're both on the same side. So opposite relative orientation. All right, moving on then, the last page here. Ozonolysis is the last reaction. So we have, they just, in this case, just want us to draw the curved arrows for the very, very first step to form the first cyclic intermediate, right? The first ozonide, as they call it. All right, so remember that pi bonds are nucleophilic. So the electrophilic oxygen is the one attached, that's neutral attached to the positive charge. That way the bond can go, the electrons from the bond go to the oxygen as a lone pair so that it's no longer positively charged. Then this would be left positively charged right next to this negatively charged oxygen. That will form a bond simultaneously, right? And so we get our first cyclic osmate. And then eventually this collapses and we end up with CO double bonds attached to each carbon. Okay, so now it says for ozonolysis reaction, break the carbon-carbon double bond, give each a carbonyl group. Predict the product of the following ozonolysis reaction. So we have, right, just break this carbon-carbon double bond, give each side a carbonyl. So this one has end up with a ketone and an aldehyde. What about this case? Right? We have breaking all of these carbon-carbon double bonds. So we end up actually with 3 products in this case. End up with simple formaldehyde. End up with this dialdehyde. And here, so in this case, because the tetrasubstituted alkene, we end up with 2 ketones. This one is going to form 2 aldehydes, but they're going to be tethered together, right? So you could initially maybe try to draw it sort of still in like a ring-like conformation, even though it isn't really a ring anymore, right? So sort of kind of like this, just to make sure you keep the stereocenters the same, something like that. Or you could, now that it's not a ring anymore, it would probably most commonly be drawn in a linear fashion, right? So we have the aldehyde, then we have 1, 2, 3, 4 carbons, and then another aldehyde. So 1, 2, 3, 4, and then another aldehyde. Right? And we just want to make sure that if we flipped one of those over to get here, then we do that. So sort of I imagine taking this one and sort of rotating it over here. So I didn't really do that one. I rotated it while keeping it in the plane of the paper. Whereas this one, the oxygen now pointing this way over. So it should be dash. And if you ever want to double check, remember that R and S always should work for you, right? So whatever it started with, it should stay that way. Otherwise, we can make a mistake. We can go ahead and double check that. So we have 1, 2, 3. 1 to 2 to 3. Our hydrogen is pointing back, so clockwise and R. Right? And then that was supposed to be this one. So I can always keep going. 1, 2, 3. Again, our hydrogen is pointing back. That's still clockwise. This is R. That's great. I didn't mess up that one. Look over here. So same priorities. 1, 2, 3. Hydrogen back. This is now counterclockwise in S. 1, 2, 3. Our hydrogen is pointing out at us. So clockwise becomes counterclockwise and still S. So we did not make a mistake there. Okay. What reagent is needed to make the following ketones / aldehydes? So remember, we really just need to identify the 2 carbons, if possible, and then just connect those as the double bond. Right? That's the easiest way to do that. So we can, on one side, we have the 2 methyls, connect through double bond, right? And then have a methyl and an isopropyl. All right, next, again, same idea. Just connect these 2 together. We can sort of start with the 5-membered ring, double bond. It's going to be connected to this carbon, which has a methyl and a bond to a cyclobutyl. And then same idea here. Zip those 2 together in a double bond. this is now going to have come from a ring because these are two pieces are attached in one structure. So whenever you're making a ring, I always like to count the carbons, right? And I like to just count the carbons that are involved in the ring. You could include the other carbons as well. It's just personal preference. I like to do it because this will tell me now how big of a ring, right, I need. So I need to make a 6. So I can just go ahead and sketch in a 6-membered ring. And then there's going to be a double bond between 1 and 6. So if I make this 1 and 6, right, then this is where my double bond is, 1 and 6. So what else is attached to 1? 1 also has a methyl. Right? 2 had a methyl. 3 and 4 don't have anything, they're just methylenes. 5 has a methyl, and 6 also has a methyl. Okay, this one is a tricky because it could have come from a couple of different possibilities, but they're giving us either a substituted cyclopentene or a substituted cyclohexene. Let's do some counting. So if I start here, it's 1, 2, 3, 4, 5, right? And then this would be all the way up to number 6. So I should connect either this one and this one for a 5-membered ring, right? Or 1 and 6 for a 6-membered ring. Okay, so cyclopentene, right? So it tells us, we just go ahead and draw it in. Cyclopentene is going to be a substituted cyclopentene. So we'll just go ahead and do that, right? That is our red pathway. So 1, 2, 3, 4, 5. Let's see what else is attached. So 1 is an aldehyde, which means there's just a hydrogen attached here. 2, 3, and 4 are both methylenes. And then 5 will add attached at carbon 6, right? Which also, by the way, needs to get attached to this here, right? So this one can either attach to number 6 or number 5. In this case, it's going to be number 6. To attach to 5 is a carbon number 6, right? Which is going to be double bonded. Let's call this carbon number 7. All right, what if it was a substituted cyclohexene? Draw that in. Cyclohexene, my blue pathway. Right, so we have 1, 2, 3, and 4 are methylenes. 5 is actually double bonded to 7 in this case. So we want to add that in. 7. And then 6 is an aldehyde, so it had a hydrogen attached as well. All right. That was probably enough work for the day. I'm sure your brain is strained. But if you made it through the activity, great work. You are doing well, and we're almost near the end of the semester, so just keep up the good work a little bit longer.